In this lesson, you will use rate of change to solve problems, and you'll also find the slope of a line. So first of all, what's rate of change? It is how a quantity is changing over time. And I'm going to give you a formula to use right here. It's going to be the change in y over or divided by the change in x, and that's going to be our rate of change. X is what we call the independent variable, and y is the dependent variable. So in this situation, we have a number of computer games, which is X, and then our cost, which is Y. This is going to be independent because the number of games just stands on its own, but our cost is dependent because our cost is depending on how many games we buy. Now, I want to know the change in Y over the change of an X. So I'm just going to pick any two coordinates here. And so what I would do is I would start with 156 minus 78 to find the change in y. These are my y's. And then I would take that same corresponding with the 156, the 4 minus the 2 for my change in x. So when I subtract, I know that this is 2, 156 minus 78 is 78. And I can keep dividing and I get 39 when you divide it out. So our rate of change is 39. And this is going to be cost, because this was cost up here, and this was our number of games down here. And if you would think about how many games are $39, that would be 1, because 39 over 1. So we can interpret this as our cost per game is $39, or our rate per game would be $39. And so this is a real-world explanation of rate of change. And rate of change is usually used with real-world problems. So I'll give you one to try in your notes. Now, you think of rate of change as always being a constant, like totally going straight uphill. But here's an example of amusement park data. This is from 2000 to 2002, from 2002 to 2004, and then from 2004 to 2006. So as you can see, I have a steep increase here, a slight increase, and then a very steep increase. So my rate of change is not going to be constant. This is going to be a different rate of change than here. So let's find those different rates of change. From 2002 to 2000, I'm going to use this data that I see here. So it's 324 minus 317, and that's going to be in millions, I believe, over. Then I take my years, 2002 to 2000, and when we divide that out, we get about 3.5, and you can check that on your calculator if you'd like. And then we're also going to find the rate of change here. And so when we do that rate of change, it's 325 minus 324, so you might already know that that's going to be 1. Over, and then that's going to be 2 as well, because it's 2004 minus 2002. So that would be 0.5, or 1/2 is 0.5. So as you can see, this is going to be attendance of 3.5 million per year. So it looks like we're growing by 3.5 million a year. Whereas here, we're only growing by 500,000 a year. So it looks like between these 2 years, we have a lot of growth, a lot of attendance. Between these 2 years, not very much. So we can have different rates of change in different areas based on the rate. So in a real world situation, you really want to look at your graph and determine what points you want to use. A rate of change is constant for a function when the rate of change is the same between any two pair of points. So linear functions are always going to have a constant rate of change, because if they're linear, we just sketch one here. If they're linear, they're going to have a constant rate with which they're going up. And that's the second thing that we're going to study today. So using that truth, we want to determine if these are linear functions or not by just looking at the points. So it would be so great if we could just look at the picture. But I'm going to tell you right now, you don't have to graph these. We can look at their rate of change. So let's just pick some points here. Is this going up by the same rate? Well, if you look, that's a difference of 2, difference of 2, difference of 2, difference of 2. You bet it is. Is this going up by the same rate? If you check here, 3, 3, 3, 3. So I'm going to say yes, this is linear because it's going up by the same rate. And another thing you could do is you could actually pick some points and do -12 minus -10 over 10 minus 7 and get the actual rate of change if you wanted to. Now let's look here. Going up by 2, up by 4, up by 2, up by 4. Well, this is going to be a no, because this is not a constant rate of growth. I grew by 2, then 4, then 2, then 4. This can't be linear, because this would go up a little, go up a lot, go up a little, go up a lot. So that is a no. And you wouldn't have to check a rate of change here. You can just see it clearly in the points. So I'll give you one to try in your notes right now. Our next definition is slope, and slope is the ratio of the rate of change in the y-coordinates, which we call rise, to the corresponding change in the x-coordinates, which we call run. So as you move from one point along the line. So we're going to say slope is rise over run. Rise over run is slope. And the formula for slope is going to be the change in y over the change in x. And this delta is what this is called. This just stands for change. And our actual formula, slope formula, is going to be y2 minus y1 over x2 minus x1. So this is the second y-coordinate minus the first, over, divided by the second x-coordinate minus the first. And we'll do a lot of practice with this so you'll get better at it. What we're going to use for slope is the letter m. The reason we do this is because the Latin term for slope starts with an M, so that's where we got it from. And to help you remember it, you can think of a mountain has slope. The slopes, if I talk about skiing, the slopes, that's mountains, and mountain starts with M. So we're going to use M for slope. M is rise over run, change in y over change in x, and here's a formula for you. So let's try that out. I want you to look here at how the slope is changing. This is going to show you the rise over run here, if you can see that with the video. You can see rise over run here, and you're going to see how it changes. This is change in y over change in x. So right now, this line has a slope of 1.5. Watch what happens. As I increase the slope, what is happening to my line? You should be saying something about how it's becoming steeper, right? Because the higher my slope is, the more steep it is. Well, let's bring it down. See, the lesser the number, the more constant the slope is. One other thing I'd like you to notice is all of those numbers were positive numbers, and my slope is going what we consider to be uphill. We read it from left to right. So this is a positive slope because it's going uphill. You can imagine yourself down here and you have to climb the mountain. If I go in negative, this is -2 is this slope. If I have a negative number, it's downhill. We read from left to right. So imagine yourself standing here, you would ride it down. So a negative goes down, positive up, negative down. So look what happens as it becomes more negative here. It goes steeper. So more negative, more positive, the steeper the line will be. Well, I'll do some more examples of that in a moment. So here's your slope formula. Here's a set of coordinates. This is going to be x1, x2, this is x1, y1. Sorry about that. This is x2, y2. So this is the first x, the first y, the second x, the second y. So plugging it into the formula, I'm going to do 5 minus 0 over 1 minus -2. Now remember how we add our integers. These are two negatives together, so they become a plus. So this is 5 over 1 plus 2, which is 3. So I would leave it as m equals 5/3. We do always leave slope as an improper fraction. We don't use any decimals, okay? Just for right now, leave it as slope. And here's why. I can see it's going to rise 5, run 3. And then I can graph it. Here's my grid. Rise 5, run 3, rise 5, run 3. I can graph my line if I can see what's going on with the rise over run. So leave it improper, that's fine. Make sure you reduce it. I mean, you don't have 10/6 or something. Make sure you reduce it, but you can leave it improper. Let's try another one. This is x1, y1. This is x2, y2. -3 minus 4 all over 2 minus -3. -3 minus 4 is -7 because two negatives make it more negative. These two negatives will make it a plus, so it's 2 plus 3, which is 5. So my slope is -7/5. So that means I'm going to fall 7, run 5. Fall 7, run 5 when I graph it. How about this line? This is going to be x1, y1, x2, y2. -1 minus -1 over 2 minus -3. -1 plus 1 is 0. 2 plus 3 is 5. So we're going to say this slope is 0. The reason we say it's 0 is if you divided 0 by 5, you would get 0. And this is what we call a horizontal line. It looks like Nebraska, okay? Because it's flat. There's no slope. It is straight across. And you have a huge clue to that. Look, our y's are the same. So we know that this is at -1, that it's horizontal. If you have the same y coordinate, it's going to be a horizontal line. And your slope is going to be 0. So would you even have to work that out? Psh, no. You could just answer it because you know the y's are the same. And this is your slope of 0. All right, what about here? Let me let you guess. The x's are the same this time. Think about what would happen. I'll go ahead and work it out with the formula though. This is 3 minus -2 over 1 minus 1. So that is 5 over 0. Try this on your calculator. It's going to say error because you can't divide by 0. This is what we call an undefined, and I just abbreviate UND for undefined. This is an undefined slope because this line is what we call vertical, and this is going to be vertical at 1. That means every single x coordinate is going to be a 1, and it is immeasurable. It's an undefined slope because you can't measure it. It doesn't have a rate. All right, moving on. So these are the 4 types of slope that you can have, and there's a great chart on page 176 if you'd like to look at that chart in your book. A positive slope, if this is my grid, a positive slope is going to appear to go uphill. Okay? You're standing here and you're climbing. It's going to go uphill. That's positive. A negative slope, here's my grid behind, a negative slope is going to appear to go downhill. So you're standing here and you're falling. You could have a 0 slope. Do you remember what 0 slope is? Do you remember? It's horizontal. It's like Nebraska. There's no slope. It's horizontal. And then you could have an undefined slope. Do you remember what undefined is? Think about it. It's going to be up and down, vertical. It's not defined because it has no rate. I cannot define it. So find the slope of a line that passes through -2, 4 and -2, -3. Hey, see? Same x. So that's a huge clue. It's going to be undefined. You try it and see what it is when you work out it in the formula. But if I have the same x coordinate, it's going to be undefined. Now, what happens if we have a missing coordinate, but we know the slope? Well, we can use slope formula. Here's a slope formula. So we're just going to plug values into this formula. Slope is 1/3. And then my y2 is r, minus my y1 is 4,